to discuss with you indeed process intensification with membrane reactors. But before that, allow me to tell you a little bit what we do in our group, who we are, and then, of course, membrane reactors are membranes and membrane reactors are a big field. So I will take a couple of examples, and in particular for large scale and for small scale use of membrane reactor. And then looking at the examples that I will give to you, I will also tell a little bit where we are and which project we are carrying out at the moment. So I'm working at TUE, Eindhoven University of Technology, which is in the Netherlands. And the Netherlands is a very, very small country, and Eindhoven is in the south. So it's close to Belgium and relatively close to Germany. As a matter of fact, it's close to everywhere because the Netherlands is a small country in Europe. And when I introduce my group, I always say our labs because I work in Eindhoven. But since 10 years now, or even more, we have a strict collaboration with Tecnalia in Spain, and especially the membrane group in Tecnalia. And with this group, we share laboratories, we have a lot of projects together, so we really present as a group. Now, if I tell you a little bit what we do, I work on integrated reactors. So what I do is integrating the reaction with some other function. And one example is a membrane reactor where the function I integrate is separation through a membrane. And today I will discuss this. We work also on other type of reactors like chemical looping is another integration of reaction and air separation in this case. So I use a metal, and this metal reacts with oxygen in the air. So it's oxidized, and you know that oxidation of metal is always exothermic. So you produce heat, and then you can use this heat to drive a reaction like steam reforming. The charm of this system is that if you do a combustion, for example, you get CO2, but you get the nitrogen leaving the reactor from another side. So nitrogen and CO2 are separated. So it's a very nice concept to achieve your reaction without the need of CO2 separation. Another reactor we work or system we work on is integration of energy in the form of plasma and reaction. So we work on plasma reactor, plasma systems. So looking at membranes or membrane reactors, in Eindhoven, we work on membrane preparation, but especially on the integration in membrane reactors. So we start from a very fundamental study. In this particular case, we use to develop a solvent that can be used in a membrane and then is driving the reaction of methanol production, sorry. But as I said, we like or we work more in the integration in membrane reactors. So this is a typical example of a small scale, is a 3D printed membrane reactor, but we also scale up. So here you see a bundle of 125 membranes for a prototype for hydrogen production. And today we will also show more figures of this. And then, as I told you, we work together with Tecnalia. They work on membrane reactor, but they work much more on membrane preparation. So you see a variety of membranes, including polymers. In our group, we don't work on polymers, we just use polymeric membranes. And they also do the scale up. So these are carbon membranes. We work on small scale, and then they scale up to larger scale, together with, for example, palladium membrane. So today we will discuss mainly palladium membrane, but what we say you can apply to a little bit everything. Now, coming back to the topic of today, I think you know this picture is quite famous. Is the concentration of CO2 in the atmosphere as a function of time, and of course you always had increase and decrease of concentration, but is without doubts, and especially for me is without doubts that with the Industrial Revolution, the carbon dioxide in the atmosphere is increasing much more than was seen before. And of course, the outcome of this is the change in climate. And of course, this is also a famous picture on the increase of ice melting. So this figure is quite interesting, not only if you are an animal activist, but if you live in a country like the Netherlands, you have to recall that if you produce water, this will flow somewhere. And if you look at the models where the water will flow, and you recall where the Netherlands is, you will see that if we don't do anything, then part of our country will be underwater very soon. So this is a driver to do something with CO2 emissions. Now, if you want to find a solution to this problem, I identify a few solutions. And the first one is to reduce the number of people. Now, okay, this is not a politically possible solution, not politically correct, but is a solution. And the other solutions are to reduce the use of fossil fuel. And this you can do in two ways, or even combining that. You can use more renewable, but you can also work on the efficiency of the processes. And if you combine the two, of course, you have a bigger impact. And then the third one is to capture the CO2. Of course, it's much easier to capture the CO2 where you produce it, but in the long term, we have to capture also from the atmosphere. Now, these are two topics where we can make, as chemical engineers, we can make a change. And these are the two topics that we have to work on. And we have to realize that if we don't do anything to these two topics, then Earth will do something with the first one. So at a certain point, the climate change will reduce the number of people. So this is the final solution that we will not like to reach. Now, so we agree that CO2 is increasing, that is a problem. Let's see who is the responsible of this. And if you look at the different reports, I took a report of IPCC, you will see that most of the CO2 emitted can be divided in roughly 4 parts. So one is agriculture, farming. Another one is in industrial production. Another part is transport. And then there is electricity and heat production. And this heat and electricity production, if you zoom in, of course, you produce electricity again for industry or for transportation, for building. So you have this 4 parts that contribute to the CO2 emissions. Now, of course, it's very fine to read a report and say, you know, there are industries that are emitting CO2, so they are the responsible. But look at it, why the industry are using energy and are producing CO2. And a couple of years ago, I was giving a presentation like this, and I went to this website here. In this website, you can answer a few questions about your lifestyle, what you do, and how much you travel, how you travel. And there will be a calculation on how much you contribute. And the results of when I put my numbers in, you would see that the results would be that if everyone would use the same resources that I use, then Earth, you will need 7 times the resources that Earth can produce in 1 year. So you see that this amount of energy that is used in industry is because of us. And then if you zoom in, you will find out that again, there are more or less the same categories that were before. So food, mobility, I had a lot of projects, so I was traveling quite a lot. And mobility, of course, was quite impacting. And then, of course, housing and goods. So these are the four parts that contribute to my consumption. But this is just to say that it's not the industry that is producing CO2 just because they want to produce it. It's the industry that is supplying to us for our lifestyle. So we are all responsible. Now, let's see how we can reduce this use of energy. And a few years ago, there was a very nice paper in Nature, which is called The 7 Separation That We Saved the World. And these numbers are for US. And you see again that also in US, except the numbers itself, the ratio is again divided in 4 parts, more or less similar. You have commercial, you have industry, you have transportation, and you have residential. So more or less the same. And in this paper, you would see that if you take only industrial, around 55% of the energy is used for separations. And if you take that, 50% of this energy in US is used for thermal separation. So distillation, evaporation, drying, absorption, and so on. And the authors of this paper found out that if you take those separation and you change that separation with a membrane, so instead of using thermal, you use pressure and physical separation, then you could reduce have 90% less energy consumption. So you see that doing the same kind of separation, but with a different separation technology, you could already reduce the energy use or reduce the CO2. Now, what is a membrane? I know that you are also learning membranes and membrane reactors, so this should be very clear to all of you. A membrane is a barrier that is selectively separating 2 phases. And recall that should be selective, because if it's not selective, it's not a membrane. Perhaps it's a filter, but it's not a membrane. And in this particular case, you see a palladium membrane that is basically able to separate hydrogen from the other gases. And I will come back to this in a minute. Now, if you look at the membranes, of course, as I told you before, there are so many possible applications of membrane, and probably the most known one is the separation. So the membrane is a layer that is separating 2 phases, and one component is passing preferentially through the membrane. Of course, there are other applications. One is contacting. So you can use a membrane to make in contact a liquid and the gas. And you know that if you do gas-liquid contacting, normally you do in a tray column or in a packed column. If you take a packed column, perhaps you can reach a contact area, specific contact area of around 500, 700 square meter per cubic meter. If you use a membrane and this membrane is nanoporous, then you can make a contact of up to 10,000 square meter per cubic meter. So you have a much higher contact and much higher exchange. And then what is also interesting is that if you play with the material of the membrane and you play with the pressure of the 2 sides, then you can make sure that the contact stays in the membrane itself, and you have no gas entering the liquid, no liquid entering the gas, which is also quite interesting for many applications. Another application is immobilization. So you can use the membrane as a support for your catalyst. And this is quite interesting when the catalyst is an enzyme, for example. And another application is a controlled release of a material. So you can use the membrane and you can tune such that you can control how much is the flux of this material. And of course, you can think about medicine like insulin, where the membrane will release the insulin depending on the membrane material and the concentration that the person needs. Of course, you can integrate all of this function with a reaction. So you can have a contactor where the reaction occurs here, or you can have a reaction here and one of the product is removed. In that case, you have a membrane reactor. So a membrane reactor, if you look at a typical scheme, is a vessel where there is a reaction on a catalyst and you have a separation through a membrane. And the separation can be that you remove a product, but can also be that you supply a reactant to your reactor. Now, of course, it looks nice, right? You integrate a membrane and you integrate a separation in a reactor, but does this pay off to have a membrane reactor? Of course, there are a lot of examples, and I took the example from one of my colleagues showing that if you take, for example, water gas shift, which is a typical reaction in industry, and you take a conventional system as reference. So this is the amount of catalyst in a conventional system. If you use a membrane reactor, you can decrease this amount of catalyst quite a lot. Of course, you have also other benefit because the separation is inside the reactor. So you have also pure hydrogen directly out of the reactor of water gas shift. So you see that there is a benefit, but you have to be careful because if you have a reactor and a separator, you can optimize the condition of the reactor, you can optimize the condition of the separator, and you can have a very optimized system. If you combine the two, of course, the membrane should work at the same condition of the reactor. So, for example, you cannot put a polymeric membrane in a water gas shift reactor because the polymeric membrane will be destroyed immediately since the water gas shift is exothermic and the high temperature water gas shift is carried out at 400, 450 degrees. So you see that you have to have the two working together. So you lose a little bit the degree of freedom in optimizing catalyst, optimizing separation because they have to work together. So to use a membrane reactor, you have to have some challenge in the reaction you want to carry out such that the membrane reactor can help you. And actually, you can identify a few challenges. If you have an equilibrium reaction, of course, you know that the maximum you can reach is the equilibrium conversion. No matter how much catalyst you put in, that is the maximum conversion that you can reach. If you remove a product, because of Le Chatelier principle, you shift the equilibrium towards the product. So this is a clear advantage. Of course, if you have parallel reaction or consecutive reactions, you can remove the product that you want and avoid that this product is further converted. So this is a clear advantage. And here you can use a membrane reactor. So there are a few advantages, and most of the cases are when there is an equilibrium or when there is a consecutive reaction. And recall that when you have an equilibrium and you can remove a product, then you can operate the reactor in conditions that are not prohibitive by the equilibrium. For example, if you have an exothermic reaction, you want to work at low temperature to get maximum conversion. But if you remove the product, you can go to high temperature and then the reaction is faster. You need less catalyst and the reactor will be smaller. Now, let me give you two examples of today, and these two examples are related to these two pictures. One is Orion, and the other one is a very famous book of Jules Verne. And if I take this in sentences, I will use these two sentences. The first one I like a lot, which is the following: hydrogen and stupidity are the two most abundant material in the universe. And I want to add that hydrogen is not concentrated on Earth. And the second sentence, is from the book of Jules Verne that tells you that the hydrogen and oxygen will be used as a source of heat and light, or heat and power. And this is very nice because it was written in 1874. So quite a long time ago. And if you look at this, looks very nice, close to fuel cell, for example, where you use hydrogen and oxygen and you can produce heat and electricity. Now, let's start with the first one. So the hydrogen production at larger scale, because we need hydrogen, but hydrogen is not existing on Earth as hydrogen gas. It's always connected to carbon or other component. So a typical process for hydrogen production starting from natural gas is something like this. So you have a couple of reactors at high temperature because converting methane requires high temperature because it's an equilibrium reaction that is endothermic. And then normally if you convert at very high temperature, you get CO. And CO, you can carbon oxide, you can convert further to hydrogen. So you have you decrease the temperature and you go to water gas shift. And the water gas shift is a low temperature because it's an exothermic reaction, equilibrium reaction. So you want to go to lower temperature. And then, of course, you have to purify hydrogen. And if you have a very big plant, then you try to recuperate all the heat, and especially the off gas you use as burner, as fuel in the burner. So what you have at the end of the day is that you feed air and natural gas, you get the pure hydrogen, and you get a lot of CO2 into nitrogen. We said before that we want to avoid this, right? So if possible, we want to find a way to avoid the CO2 here, which means that we have to find a way to supply the energy to the reformer in a better way. And we want to make this more efficient. We want to combine separation and reaction. So let's start with the first point, to supply the heat to the steam reformer. And a very elegant way to do this is to use the chemical looping, what I mentioned you before. There are different ways, but I like this one the most. The chemical looping is using a metal, which is reacting with air and is producing a metal oxide. But this reaction, as I told you, is always exothermic. So if you take iron, for example, and this iron is just outside, is producing iron oxide, right? That reaction is extremely exothermic. Of course, if you touch the rust, you are not burning, simply because it's a reaction occurring at low temperature. So it takes a lot of time. But if you take the same iron and you bring at 600 degrees, then that reaction is extremely fast. So you can use the heat because you produce a lot of heat at the same in small amount of time. And this is what we do in chemical looping. So the metal is combusted or oxidized to metal oxide. And this metal oxide is very hot, so you use the heat to drive a reforming or a combustion of the fuel. Now, suppose you do a combustion just for simplicity, and suppose you make a black box around this chemical looping. What you have is that you feed air, you feed the fuel, and you produce CO2 and water, and you produce nitrogen, right? It's a combustion of the fuel. But if you look at the system, you have the CO2 leaving from one side and the nitrogen leaving from the other side. So all in all, you have the combustion, you have the same product, which is heat, but the nitrogen and the CO2 are separated. So you don't have CO2 emission in the atmosphere. Now, this will solve the first part. The second part, of course, will be a membrane reactor where we have a membrane that separates the hydrogen, and put together becomes this very nice concept. This was a concept that I developed in a national project. And when I started in 2012, it was just an idea to do this combination. And in 2017, we did the demonstration, and I have some picture of the setup later. And you see that indeed, I use the membranes, so I produce pure hydrogen. Then I use a metal that is oxidized, so nitrogen is leaving from this side and CO2 is leaving from this side. All in all, pure hydrogen with CO2 separation, so no pollution. Of course, you have to prove the concept if it's working. So we did a setup. Here you see a few pictures of the two reactors, the riser, then the separation of gas solid, and then the solid goes back in this reactor here, so from the top. And from the top, we have also the connection of the membranes where we can remove the hydrogen. And the solid, of course, then is coming back here. This tube is connecting the two reactors you see here. So the solid is circulating between the two reactors. Of course, we develop membranes, and we use palladium membranes because palladium, if it's a dense layer, then is able to separate only hydrogen through the layer. So we developed this palladium layer membranes with Technalia, and you see that this palladium is very, very thin. So it's around 4 to 5 micron. So we put in the reactor, and I want to show you only a few experiments. You see here almost 1 hour of experiment. And what is nice is that this is steam reforming, and steam reforming of methane generally is a very fast reaction. So you see that when we start, immediately we reach, after less than 1 minute, we reach the equilibrium conversion. So the hydrogen is stable, the methane is stable, and if you do the calculation, this is the equilibrium. And then we open the membrane, so we start to remove some hydrogen, and immediately the methane becomes lower, so you go above the equilibrium of a conventional system. So it's very nice to show. Then what you see in this graph is that you have also a lot of fluctuations. And normally when you have fluctuations, it's not very good for your system, but in this case it's very good for us, because this fluctuation in temperature is telling us that the solid is passing in that point. And if the solid is passing in this point, where this thermocouple is, then it's basically going to the other reactor. So you have the circulation of the solid. The moment that this temperature is uniform, like the green one, then it means that the solids are not moving. So you don't have chemical looping anymore. So this is a few examples of experiment. And of course, you use the experiment for 2 reasons. One, to prove the concept. The other one, also to get the data for your model. And then once you have the data, you can integrate, make the design and making a process design. And when you make a new reactor, as I told you, looks always nice. But what is telling you if the reactor is good is when you do an energy analysis and the cost analysis. So what you have to do is a modeling of the complete system, because the reactor can be very nice, but perhaps the final product will be much more costly. So nobody will use this reactor. And here I want to tell you something. When you do a process design and you compare with another system, you have to be fair. You have to be fair in the sense that the feed of the new system should be in the same condition of the old system, and the products in the new system should be in the same condition of the other system. So if you take a conventional steam reformer, the hydrogen is produced at high pressure. If you take a membrane reactor, since the flux through the membrane is driven by a delta P, of course, hydrogen will be produced at low pressure. So you have to also add the compressor. If I don't put this compressor here, basically this hydrogen will be, I could say that is much cheaper than the steam reformer, but it's not true, because you have to put the compressor and you have to calculate the efficiency and the electricity that you use. Anyway, we did this, and we did with Aspen. If you use Aspen or ISIS, you know that this software do not have models for very complicated reactors. And membrane reactors are relatively complicated because you have also the separation inside. So we develop also our own model for Aspen. You see, if you know how to use Aspen, this is a typical picture that you know in Aspen. And you see that here now we have also our membrane reactor models. And of course, once you have this model in Aspen, it's very easy to do the energy analysis. And if you do the energy analysis and the cost analysis, then you come out with this final figures. And what you see here is that if I take a conventional steam reformer, I have very high efficiency. Of course, I don't capture any CO2. CO2 is just going in the air, so I don't have CO2 avoided. And the typical cost is this one per cubic meter of hydrogen. Of course, in this cost, it depends on the cost that I put for methane and the cost that I put for electricity and for steam and so on. And the same cost I have to put in all the other calculations. Now, if you take this conventional system and you want to capture the CO2, this is possible. Why people don't do it? Simply because it's costly. So the efficiency, the total efficiency drops from 80% to 67%. You can avoid up to 75, 80% of the CO2. So much better, but this has a cost. So the hydrogen, instead of this, will become this one. So much more costly. And if you do with the new system, of course, the efficiency is similar. You can capture much more CO2 because in principle, you don't have mixing of CO2 with nitrogen. This is not 100% because I'm still using electricity for the compressor. And you see here that if I would not put the compressor, this will go to 100%, but it's not fair. And the cost is very similar to the cost of the conventional one, but at the end of the day, you have the same cost of the product, but you don't have CO2. So very, very nice new concept for a scale up. Now, of course, there are some challenges. And one of the challenge is the stability of the membrane, because the concept that I show you is a concept where I use a fluidized bed. The particle have to move around, and also is a relatively high temperature, 550 centigrade, more or less. And you see here that if you take our membrane, this is the selectivity, this is the flux. The selectivity is relatively stable, but when you go to higher temperature, you see a small decrease of flux and the selectivity, which you would expect a flux to increase. So something is happening on the membrane. And at a certain point, after 800 hours, the selectivity goes from 170,000 to 2,000. And of course, the target is around 10 to 15,000. So we are much better than the target, but after 800 hours, we go below the target for the purity of hydrogen. And if you do a zoom on the membrane, you see that there is some change occurring on the membrane. And this is due to the fact that we work a lot at high temperature, the palladium becomes more mobile, and we have also fluidized bed. So this is a big challenge, but of course, we are doing research, so we like big challenges because this become research questions. So we spend quite a lot of time to produce a membrane that withstands temperature, but especially fluidized bed. And basically what we did is a new membrane, which is we call double skin. This is a picture of this membrane. Basically, you have a support, and then you have your layer. If you stop here, basically this is a conventional palladium membrane. What we did, we put a protective layer on top of it, which is porous enough to have no mass transfer limitation, but is dense enough such that particles are not touching the palladium. So the separation is done by the palladium, but the particle of the fluidized bed will never reach the palladium. And does this work? The proof is here. Here you have a conventional membrane. Again, you see that the conventional membrane for almost 400 hours is stable and then starts to decrease the selectivity. And again, you go from, let's say, 10,000 at the beginning to 1,000 at the end. And if you take the new membrane, again, the first 400 hours stable, but then it remains stable for much longer time compared to a conventional membrane. So this conventional membrane was same type without the protective layer. So in principle, we found a way to save the membrane. Good, this was for large scale. Now allow me to give an idea of how you can use membrane reactor at small scale, and especially coming back to hydrogen as fuel for heat and power. So we worked quite a lot on combined heat and power production. And what is the idea behind it? This picture is for US, but I guess for any country will be the same. Normally in your house, you have a boiler where you produce hot water or the heat that you need for heating up the house. And then you get the electricity coming from the grid. And the point is that somebody else is producing the electricity and is transporting the electricity to you. So this transportation is with a lot of losses. So what you have that if you have to produce in total, let's say in this case, 85 kilowatts, at the beginning you use quite a lot, much more kilowatts. You use 189. So you have a lot of losses, and most of the losses are in the transportation of the electricity. The boilers that we have at the moment in our houses are quite efficient. So there is not much that you can recover here, but you can recover quite a lot in this part. And the idea is that instead of producing electricity somewhere and transporting the electricity, you could try to produce the electricity in your house. And every time you produce electricity, whatever system you use, you also have as byproduct heat. So you can produce the electricity and use the heat directly for heating up the house or the water. So this is called combined heat and power. And of course, since there is no losses of transportation, then of course the efficiency is much higher. So you see that you use much less fuel. And if you use much less fuel, of course, less CO2. So the idea was to use a combined heat and power. And there are different ways to do that, but we selected the way to use a fuel cell. And the fuel cell will require hydrogen. And just to give you a few points, we started with a European project, and then we had 2 or 3 European projects in a row to develop this system. Just to tell you what we did in this project, since we want to use a fuel cell, a PEM fuel cell, we start from natural gas and we have to reach the hydrogen. And of course, you saw already at larger scale how the system looked like. You have a high temperature reforming, then you have a water gas shift, and then you have the purification. So this is a conventional system. The nice thing is that for combined heat and power, there are companies that are already selling machines where all this is integrated. So reforming, shift, removal, and PEM. So you can buy machines that starts from natural gas and water and give you heat and electricity. So these are commercial. What we want to do is to change the system. Instead of having all these steps, we have only a membrane reactor. And we start with a reefer cell just to test with basically methane. And then to ferret, we start using different natural gas in the different countries, because each country has a different quality of natural gas. So we show that the reactor can work with different natural gas. And then for fluid cell, we did off-grid application. So instead of using natural gas, we use ethanol or bioethanol. And just to show you how the system changes, this is a conventional system that is on the market. And if you use a membrane reactor, of course, the fuel cell should be there, the heat recovery should be there, but you can change quite a lot the initial part where you have the reforming, and you can get rid of a few systems here, water gas shift and purification in particular. Now, if you want to do a comparison, I just divided this in 4 stages. And you see that in the fuel processor, of course, you have all the reactor and separation. And if you do the new system, of course, if you divide in the 4 section, this system is more or less the same. The fuel cell is more or less the same. This is a little bit different, and this is completely different. So you can see where the gain in efficiency and in cost is. And now I want to give you only the results, because also in view of time, if you calculate the efficiency, let's look at the electrical efficiency of the conventional system is 34%. And this is quite nice, because this is the calculation that we did. But if you go in the market and you see the different products that are on the market, the efficiency, the electrical efficiency of those products, as specified by the vendor, is between 32 and 35%. So it means that our calculation is not very far from what is on the market. Actually, it's exactly what is on the market. And then if you do the calculation of the new system, you get 43%. And now, of course, if you compare the 2 systems, you see that in one system, in the new system, you have only the membrane reactor. Here you have a lot of reactors. But if you look at the efficiency gain is not coming by the fact that you have a single reactor instead of 3 or 4. All the efficiency comes by the fact that since you use a membrane and you shift the equilibrium, you can get the same conversion at lower temperature, which means that you have to heat up the system at lower temperature. So you use less fuel, you burn less fuel to reach this temperature. So all this efficiency is coming because in the conventional system, the reformer has to work at very high temperature, and in a membrane reactor, you can work at 600 and actually even lower at 550. So this gives you just the delta T gives you a jump in efficiency, in electrical efficiency. And this 9% is quite a big jump. If you consider that years and years of working on turbines, for example, will give you just 0.5% efficiency gain, this is quite a jump in efficiency gain. Now, let's see how the history of all this work that we did in the last 10 years. So as I told you, 10 years ago, we started together with Tecnalia working on the membrane. And of course, we start with a very small membrane. The first was 2 centimeter, and then during 2010, we reached 10 centimeter membrane. And then we went in the years to have longer membrane. We start to work with many membranes in a system. And then in 2014, we had the first breakthrough. We produced a fluidized bed for hydrogen production, and it worked for more than 1,000 hours continuously, producing hydrogen at the fuel cell level, so less than 10 ppm of CO. Then we scaled up the membrane again. We went to ethanol, and then we did much more membranes, as I show you, and we start producing also prototypes to bring to the market. So in 2019, we reached the design and construction of this big prototype. In the meantime, we had quite a number of European projects, Spanish project and Dutch project, where we worked together. And if you want to do this in pictures, it's always nice to do in pictures. These are the first membranes we were producing. You see that very small one. And then we reached the first 10 centimeter membrane. And of course, you have to also be able to integrate the membrane in the reactor. So we were working also on the sealing of those membranes. Then we start with a small reactor. And finally, we could put 20 centimeter membrane, many of them in a single reactor. And as I told you, this is the first very good application where we get... Can you see my screen still?
Yes, it's clear.
Okay, no, because there was a message. Anyway, we reach a lot of hours, almost 1,000 hours with selectivity very high, so we could use the hydrogen directly in the fuel cell. Then we did a Pullman scale up, so we need longer membrane. We put a lot of membranes together, and then we worked on really scaling up, making longer membrane, also closed from one side, which means that you don't need to seal from the bottom. And then many more long membrane together, 5, 7, 125 membranes. And then you see that the reactors from the very small one becomes bigger and bigger. So this is the 20 cubic meter per hour. And of course, we didn't stop there, because the membrane reactors, you can apply for different applications. Now there is a company, we created a company to sell those membrane reactors, but we are still working on different European projects. These are the last one we are working on. We have we are producing also hydrogen and CO2 capture in the same reactor. We are using membrane reactors to convert the CO2 to DME, or to convert C3 in products. We are making membrane reactors to produce hydrogen from ammonia. So you use ammonia as hydrogen storage material. And we have also very big projects. One is InnoMem, is a very, very large project. What is nice is that puts together 32 partners working on membrane. But what is even nicer is that in this project, we have an amount of money, I believe it's around 4 million euro, that are available for other small companies if they want to test some of the membranes for an application. So if you have an application like water treatment, you can come to us. Soon there will be some open calls for that. And you can say, can I use this membrane for this application? And the project will pay for that, at least the first couple of years. And then Macbeth is a very large project. We have 5 membrane reactors at TRL7. TRL7 means that are prototypes, these very big prototypes, as I show you. So we have 5 of them being constructed, and TUE, our university, is building one of these. And with this, I think also in view of time, I finish for today, and I hope you enjoyed the presentation. And if you have any question, you can always contact me.
Thank you very much. It is very interesting concepts and very interesting achievement.
Yeah.
Hello. Yeah, thank you very much for your nice presentation. They are very interesting and very valuable concepts and results. Actually, I am very happy to see these results. You know, our students are hearing me now. So you remember that we are talking about the membrane reactors and how they enhance the reactions and increase the selectivity, for example, about 40%, for example, or 40 times comparing to the normal blood flow reactor, for example, as we did in our last lecture on Monday. Actually, I did also some work maybe related to this in the past years, but we didn't continue because of our shifting to other projects. So we did some research on water treatment and the production of hydrogen from water by, I mean, we use couple results to get hydrogen production from water and also to reduce the salinity or the hardness of water for a step of desalination, for example, and to make use of the hydrogen produced by using it for other applications or for energy, for example. So at that time, I faced the problem that the hydrogen produced need or should be taken outside the reactor. We used a small tubular reactor. So we need to shift out the hydrogen outside. And this results of your research is very interesting for solving my problem in this I am working on. So maybe I hope that we can talk about this later on for more collaboration, because you used what you called it, or it is normal, fluidization. So in that work, I reached a point that we, a breakthrough for us, that we have what we call it self-fluidization. So we make the catalyst or the particles to move from themselves, the self-fluidization. I cannot share the screen. Maybe later on I will send you a video that shows the self-fluidization of the particles inside the solution. At the same time, we produce hydrogen and reducing the salinity of seawater. So maybe this is very, very good point that we can collaborate on for next projects, and for you, the test that you said we can test your membranes. So maybe it is very interesting idea that we can visit you and have some collaboration on testing this, our system using your membrane and using your apparatus. Now I want to, here are you. You want to say something? Now I want to open the floor to our students and our guests if they have some questions. So if you have a question, please raise your hand and ask, please. Any question, please, our guests, our colleague, our students. If someone wants to something, please raise your hand. No question. So it is for me, and also I think for our colleagues and students, is very, very clear. We have Dr. Ihab, Professor Ihab Shamali. Can you please open, please? Professor
Hello.
Shamali. Yeah, Professor Shamali, please.
Yeah, can you hear me?
Yes.
Good. I tried to actually unmute myself, but obviously I couldn't. That's why I raised the hand. But I was looking for where the hand raising is also. Professor Galucci, thank you very much for this talk. It was very nice, very useful, very helpful. Okay, I have a quick question. I come from a chemistry background. I'm a professor of chemistry in the University of Jordan. My question is, or it's actually maybe general question, it's about the challenge in storage, in the storage of hydrogen, produced hydrogen in, say, automobiles, like in moving things. So where are we now? Or where are you now in the storage problem? So we can use that in cars, in buses, in planes, in ships, in general. We've been hearing about this for years, that we're using hydrogen. Hydrogen is cheap. Hydrogen is clean. Well, they claim it's clean. The dangerous of hydrogen is to produce it on site. Like, for example, from solar energy, direct in a car, in a moving car, you produce hydrogen and you burn it, so you don't have to do much storage. Where is the help of membranes in this matter?
Yeah, that's a very good question. Of course, there is not a general answer for the storage, because it depends really on which kind of mobility. For example, personally, I believe that in the car, if you have a car, you will never have on-site production in the car. I really believe that the only possibility is to have storage, perhaps with very porous material, but still in high pressure storage. Because if you look at the footprint of the reactors, you can decrease, but you cannot decrease so much that you can put in the car. So it's something. Of course, there are people working on on-site generation, but I don't believe that will be a possibility. On the other hand, if you go to airplanes and if you go especially to marine application, there is the other way around. I think you will never store hydrogen per se. What we are working on is storing hydrogen in a molecule and then convert the molecule. So, for example, for marine application, we are working on storing hydrogen in either ammonia or methanol, because these are much easier to transport, and then to convert on site, because then the footprint of the reactors are relatively smaller compared to the complete space that you have. So it's much easier to store hydrogen in a liquid form. So as I said, it depends really on the application. Then, of course, there is also hydrogen for fuel cell for stationary applications. In that case, most probably, not most probably, I'm sure 100% that we will store hydrogen in the form of a liquid. And we are working on, again, ammonia or formic acid, for example, which you can easily convert to hydrogen and then use the hydrogen for fuel cell.
Okay, can I like do another question quickly?
Yeah.
Of course, maybe the way to go first is to go hybrid, like not to rely on hydrogen gas as a fuel in cars. We can, like, you know, like how hybrid cars started. Now electric cars are more common, so maybe this is the way to go. Now I have a question: how much membranes can store hydrogen? Like, how much hydrogen maximum can be stored? And maybe this is also a challenge in your research field.
Yeah, no, of course, when we use the we don't use the membrane as storage. The membrane is just for separation. if you take palladium, basically palladium can accommodate 940 times the volume in hydrogen, so quite a lot. So there are people using nanoparticle of palladium to store hydrogen, but in our case, the idea is to use the membrane to separate. So basically, you produce the hydrogen, you separate as pure hydrogen, and then this hydrogen goes to a fuel cell, for example, or to a compressor for a car. So the membrane is really to separate the two phases and not to keep the hydrogen inside. You can keep in the membrane, but would be quite expensive to create a membrane just for that application. And I'm quite sure that if you store and then you decrease the temperature, because if you want to store for a long time, of course, the temperature will decrease. You cannot keep the system at high temperature. And then the membrane will be broken, exactly because of so much hydrogen staying inside the matrix.
Okay, thank you again. Thank you. I was looking in the last slide, the one you're presenting now. There's thank you in all languages except in Arabic, or I cannot see it. It's a shukran.
Okay, so sorry. I should find a right one. I just look on Google.
Thank you very much again. Grazie.
Thank you.
Maybe I will send you one shukran. You can put it also. Yeah. Any other question, please? Any other question, please? At the end of this meeting, I would like to thank you, Professor Gallucci, very much for your kind acceptance of our invitation to give us this very nice and very valuable, very helping presentation. And we wish you every success in your work. And we are looking in the future, in the near future, to collaborate with you. And also, if the borders open, we can visit you. And also, you are very welcome to visit us, our university, Tafila Technical University, and my group here in the university. We are working in many topics, and I will send you my CV for more collaboration, inshallah. So thank you very much. And
thank you for the invitation, and hopefully we can travel soon. So you are welcome, but I would like to visit you as well.
Thank you very much. Thank you.
Have a nice day then.
Thank you.
Thank
Bye-bye.
you. Bye.
Thank you very much.
Thank you so much. Thank you for your speech today. Thank you.
Thank you. Bye.